JMB, how are you all? I hope you all are doing great. Welcome back to my YouTube channel. My name is Ranpara. I am a PhD scholar in the Department of Chemical Engineering at the Indian Institute of the Technology, Roper. So in today's lecture, we are continuing the solution of the industrial example discussed in the previous lecture, lecture number 13. So let's get started. I request you to please read the question. The question stated as the reaction A is converted into the new product B is to be carried out isothermally in a continuously flow reactors. The entering volumetric flow rate mu naught is 15 cubic decimeter per hour. Naught Fa is equal to Ca into nu. For a constant volumetric flow rate, nu is equal to nu naught, then Fa can be written as Fa is equal to Ca into nu naught. Also, Ca naught is the ratio of initial molar flow rates Fa naught divided by initial volumetric flow rate nu naught. The value of Fa naught is 6 moles per hour. The value of initial volumetric flow rate nu naught is 15 cubic decimeter per hour. If we solve, the initial concentration of reactants A is 0.4 moles per cubic decimeter. Now the question stated has we need to calculate the volumes of CSTR, PFR, batch, packed reactors necessary to consume 90% of A, that is Ca is equal to 0.1 Ca naught, when the entering molar flow rate is 6 moles per hour. Assuming the reaction rate minus Ra is the A is first zeroth order reaction, right? B is first order reaction, right? So in the previous lecture, lecture number 13, we have solved the zeroth order reaction case, right? Now in today's lecture, we are going to solve the B part, right? So the B part represent the first order reaction kinetics, where the given rate law is minus Ra is equal to Kca with K is equal to 0.0002 second inverse, right? Okay, so we need to calculate the volumes of the reactor. Okay, so let's say in today's lecture we'll keep all the operating parameters to be constant. We will we'll apply the performance equation of the batch reactors, continuously starting reactors, plug flow reactors, packed bed reactor, right? we'll we'll use the first order reaction kinetics, and we'll try to compare the volume, the space time, the weight of the kettle is required in order to achieve the desired conversion of 90%, right? So let's get started. So in the first case, we are solving for the CSTR, right? So by keeping all the operating parameters to be constant, right? By using the first order reaction kinetics, where the given rate law has minus Ra is equal to Kca, right? For the given reaction when the reactants A are getting converted into the new product, okay? Where the rate constant K is equal to 0.0002 second inverse, right? The first step is to write the performance equation of the CSTR. The performance equation of the CSTR is represented as volume divided by Fa naught is equal to Xa divided by minus Ra is equal to tau upon Ca naught, right? So let's say from these correlations we have two unknowns, right? Which is we need to calculate the volume of the reactors, right? Industrial volumes of the reactor in order to achieve the 90% conversion, right? So volume is unknown to us. Okay, we have the value of Fa naught. Fa naught value is 6 moles per hour. Okay, we have the value of conversion. Conversion is 0.90%, right? The desired conversion is 90%. So we have the value of conversion. Minus Ra can be written as K into Ca. We have values of K and we have value of Ca. Ca is equal to 0.1 Ca naught. And we have the value of Ca naught, 0.4 moles per cubic decimeter. Okay, so we have the values of Ra. Tau is the space time, is the ratio of volume to its volumetric flow rate. So here the unknown is volume. So due to those reasons, we also have unknown variable as space time, right? Ca naught value we have is 0.4 moles per cubic decimeter, right? So from this performance equation, we'll try to use these correlation, right? And we'll try to make the subject as volume, okay? Because we are trying to calculate the volume of the CSTR required in order to achieve the 90% conversion for the given first order reaction kinetics, where the rate law is minus RA is to KCA for the given reaction, where the reactants A are getting converted into the new product B, right? So let's say from here, by using the performance equation, we are trying to make the subject as volume. So volume is equal to Fa naught into XA divided by minus RA, right? Now we are trying to modify and formulate the equation, right? So let's say Fa naught can be written as it is, XA can be written as it is, but RA can be modified as minus RA is equal to KCA, right? So we are replacing RA with KCA, okay? I hope you have understood. So for the, we are modifying it as the numerator will remain as it is. So Fa naught into XA divided by K into CA, right? So here CA. So let's say here CA is equal to CA naught into 1 minus XA. Okay. So this is exactly why the students will get confused, right? Because we have two forms of CA. The first form of CA is equal to 0.1 CA naught, which is given in the question, right? CA is equal to 0.1 CA naught, and we have the another form of the CA which represent CA is equal to CA naught into 1 minus XA, right? Which means, so we need to understand the both the terms independently. Okay, so let's say the first form of CA which represent CA is equal to 0.1 CA naught, which means, so here we need to understand the individual terms. CA represent the concentration of reactants A. Okay, CA naught represent the initial concentration of A, which is feeding to the reactor via inlet stream, right? So initial concentration of reactants A, which is feeding to the reactor CSTR, right? XA represent the conversion, right? The fraction of conversion, right? How much reactants has already reacted, how much reactants have converted. Okay, so XA represent the conversion of the reactants into the new product, the fraction of conversion, right? The CA represent the final moles, the final molecules or the final reactant present or which is exiting through the outlet stream of the continuously starting reactor, right? So the first form represent the concentration of reactants A, which is exiting through the outlet stream of the CSTR, okay, which is 10% of the initial concentration, which means 0.1 indicates the 10% of initial concentration CA0, right? Let's say for example, in the question we have that we have the conversion of 90%, right? Which means let's say initially we are feeding 100 molecules of reactant CA0, right? So initially we are feeding 100 molecules of CA0 into the reactor. In reaction environment of the CSTR, the reaction will take place. The conversion of reactants into the product takes place, right? So we have 90% conversion, which means out of those 900 molecules, 90 molecules of reactants of A will get converted into the new product, right? Which means we are left with the 10 molecules of reactants, right? Which means we have 10 molecules of unreacted reactants which will exit through the outlet stream of the CSTR, right? So the final concentration of unreacted reactants or the final concentration of reactants A is 10% of the initial concentration, right? 10% of the 100 molecules, 10 molecules remains unreacted and will exit through the outlet stream of the CSTR, right? I hope you have understood. So this form we have understood, right? Now we'll understand the second form of the CA. So CA is equal to CA naught into 1 minus XA, which is the fundamental relationship and is always correct, right? For a single reaction where the reactants A are getting converted into the new product B, right? So the second form of CA is equal to CA naught into 1 minus XA also represent the conversion, defined as conversion, right? Okay, so now whenever we want to derive the rate, the reaction rate, the design equation or the performance equation, we'll always try to utilize the second form of equation, CA, right? CA is equal to CA naught into 1 minus XA, okay? in order to derive the performance equation, okay, we'll always try to use the second form of CA, okay, and we'll never use the first form, right? We'll not use the first form. So I hope this was exactly where the students get confused, right? And so I hope you understood. I will make you very simplified way to understand, to make you understand, right, which form of the CA we need to use, right? So we'll use always second form of the equation. CA is equal to CA naught into 1 minus XA in order to derive the rate, in order to derive the equation for the design equation or the performance equations, right? So we will use second form of CA. CA is equal to CA naught into 1 minus XA, right? So let's say here similar way we have FA naught is equal to, so we are keeping the same numerator, right? In numerator the FA naught and XA will remain as it is, but in denominator in K will remain as it is, right? In the place of CA we are substituting with its value. CA is equal to CA naught into 1 minus XA, right? So CA can be written as CA naught into 1 minus XA. Okay, now we have all the values of these terms, right? We need to just plug in all the values. So FA naught we have as 6 moles per hour, 6 mol, so volume of the CSTR is equal to FA naught. FA naught has 6 moles per hour into conversion XA has 90%, 0.90 divided by K. K, we have the value of K has 0.0002 second inverse, right? 0.0002 second inverse into CA naught. CA naught value we have as 0.4 moles per cubic decimeter into 1 minus XA. So 1 minus XA is 0.90. Okay. So I hope here up to here we have plugged in all the values, right? But we need to also confirm the unit conversions, right? So let's say here in the numerator we have moles per hour, right? In denominator we have second inverse moles per cubic decimeter, right? So in the numerator, from the numerator and denominator we can cancel off the moles, right? Now we are remaining with the hour, second inverse and cubic decimeter, right? So in the numerator we have hours in denominator, so hours will go to the denominator, right? So here hours can go to the denominator, right? Similar way in denominator we have moles per cubic decimeter, right? So denominator to its denominator will go to the numerator, right? So due to those reasons the cubic decimeter we can write in the numerator, right? And second inverse, similar way second inverse will come to the numerator. Okay, so here, so we are left with the this cubic decimeter in the numerator, we have seconds in the numerator, and we have hour in the denominator, right? So in order to make the unit conversion, we are, in order to obtain the value of volume in terms of cubic decimeter, we need to multiply with, in 1 hour we have 3600 seconds, right? So we are multiplying by this term, 1 hour divided by 3600 seconds, right? So here from the numerator seconds and from the denominator seconds can be cancelled off, right? The hours can be cancelled off from the numerator and denominator, so we'll remain with the cubic decimeter in the numerator, right? I hope you have understood. Now I request you to please calculate this, so you will get the answer as volume of CSTR is equal to 187.5 cubic decimeter, which is equivalent to 187.5 liters, because 1 cubic decimeter is equal to 181 liters, right? So here we have 187.5 cubic decimeter is equivalent to 187.5 liters, right? Which means by using the CSTR, by keeping all the operating parameters to be constant, by using the CSTR, by solving it for the first order reaction kinetics, right, for the given reaction where reactants A are getting converted into the reactor into the new product B, by using the CSTR we required 187.5 liters volume of CSTR in order to achieve the 90% conversion, right? I hope you have understood. Okay, now we know how much volume, how large volume of CSTR is required, right, in order to carry out the first order reaction, okay, in order to carry out the reaction, and in order to achieve the desired conversion of 90%, right? We have calculated the volume, right, which is 187.5 liters volume is required, but we don't know how much time will it take in order to achieve the desired conversion, right? So let's understand that and calculate. So by using the space time, we can calculate the time required in order to process 1 liter volume of the feed. It's all the space time, right? So space time is the ratio of volume to its volumetric flow rate. So volume is 187.5 liters, right? 187.5 cubic decimeter divided by volumetric flow rate is 15 cubic decimeter per hour, right? So similar way, from the numerator and denominator, we can cancel off the cubic decimeter. We are remaining with the hour, right? So after solving these, we'll get the answer as the space time of CSTR is equal to 12.5 hours, right? I hope you have understood. Which means by using which means by keeping all the operating parameters to be constant, by using the first order reaction kinetics, where the given rate law has minus RA is equal to KCA, right? And for the given reaction where reactants A are getting converted into the new product, right? By using the CSTR, we required 187.5 liters volume of CSTR and 12.5 hours of space time, right, in order to achieve the desired conversion of 90%. I hope you understood, right? So I request you to please make all the notes, right? Okay, now let's say we'll solve the another part. Okay, now let's say what if I use plug flow reactor instead of CSTR. Now what will happen, right? Let's calculate, understand and analyze. Okay, so let's say similar way, we are keeping all the operating parameters to be constant. We are using the same first order reaction kinetics, right? We are solving for the volume of the reactor, the space time, okay, by using the plug flow reactor, and we'll try to compare. Okay, so let's say for the plug flow reactor, the first step is to write the performance equation of the plug flow reactor. The performance equation of the plug flow reactor is indicated as V is equal to F naught integration of 0 to XA dXA upon minus RA, right? Okay, so let's formulate the performance equation. Okay, so V is equal to Fa naught integration of 0 to XA dXA upon minus RA can be written as, with the given rate law, minus RA is equal to KCA, because we have the first order reaction kinetics. The first order reaction kinetics is defined, is given by the rate law as minus RA is equal to KCA, right? So we are substituting minus RA with the KCA, right? So V is equal to Fa naught integration of 0 to XA dXA upon KCA. The K here we have the constant, right? The rate constant value is constant because K is equal to 0.3502 second inverse. Due to those reasons, we are taking K out of the integral, right? So we'll get the formula as Fa naught divided by K integration of 0 to XA dXA upon C. Now again, what form of CA we need to utilize, right? So this is exactly where the students get confused. Okay, so similar way as we have understand here, we'll utilize the second form of the CA, right, which is the fundamental relationship and is always correct, right, which is defined as conversion. And by understanding this CA is equal to CA naught into 1 minus XA, we can understand the concentration of reactants A at any point in the reaction environment of the plug flow reactor, right? So similar way, we will use the second form of the CA, which is given as CA is equal to CA naught into 1 minus XA, is also defined as the conversion. Okay, so for those reasons, we are writing CA as CA naught into 1 minus XA. Okay, so and we are taking CA naught out of the integral. Why? Because CA naught represent the initial concentration of A. Initial concentration of A is equal to 0.4 moles per cubic decimeter, right, which is constant. Due to those reasons, we can take CA naught out of the integral, right? So we'll get this form of the equation, which is fa naught divided by k ca naught integration of 0 to xa dxa upon 1 minus xa, right? I hope you have understood. Now we need to calculate the integral form of the, we need to calculate this integral form, right? So how to calculate? So I'll make you understand in very easy, right, in a systematic manner. So let's say in order to calculate this integral form, 1 minus xa can be written or can be represented as y, right? So y is equal to 1 minus xa, okay? So now the second step is to differentiate on both the sides, right? So if we differentiate y, so we'll get dy. Now we need to differentiate individually, right? So differentiation of 1 is 0. So differentiation of xa is dxa, right? So finally we'll get as dy is equal to, minus will remain as it is, so minus dxa. Okay, I hope you have understood. Okay, now let's say we will use these forms into the solving of the integrals, right? In this integral, right? So integration, so let's say integration dxa can be written as minus of dy. Minus can be shift to the left hand side, right? So dxa is equal to minus dy. So dxa can be written as minus dy. Okay, 1 minus xa can be written as y, right? So integration of minus dy by 1 minus xa has y. So integration of minus dy by y from limits 0 to xa. Now this is the second position where the students get confused. What limits we need to utilize, right? So let's say here we have the limits from 0 to xa in terms of xa, right? So let's say we'll understand how to apply the limits. Okay, how y is equal to 1, the lower limit came, and how y is equal to 1 minus xa, the upper limit came, right? So let's understand that. So let's say y means what? Y represent, y denotes as y is equal to 1 minus xa. Okay, now let's say here we have 0, right? In the lower limit we have 0. Okay, which means in the initial, before starting the reaction, when we have the conversion to be 0, right? Because there is, the reaction has not yet started, right? The reaction has not yet started, so the conversion of reactants into the product will be 0. Due to those reasons the conversion is 0, okay, because the reaction has not yet started, right? So conversion is equal to 0, so we will remain as y is equal to 1 in the lower limit. So due to those reasons we are writing the lower limit as y is equal to 1. I hope you have understood. Okay, now let's say what the term xa in the upper limit indicates. We need to understand that first of all, right? So here in the upper limit, xa represent the fraction of conversion of reactant A at an instant of time, right? At any instant, what is the fraction of A that has converted? What the fraction of A that has reacted? It's called the xa, right? So let's say so due to those reasons, we can write the upper limit as y is equal to 1 minus xa, which means these represent, y is equal to 1 minus xa represent the fraction of unreacted reactant A, right? Y is equal to 1 minus xa represent the fraction of unreacted reactant A, right? That is still remaining to react. Okay, I hope you have understood. Okay, so due to those reasons we can write y upper limit as y is equal to 1 minus xa. Okay, now after solving this, let's say we have integration of minus dy by y. So let's say minus sign we can take out of the integration, right? So integration of dy by y is ln of y, right? So minus ln of y from the limits y is equal to 1 to y is equal to 1 minus xa. Now we need to solve that. So let's say we are keeping minus sign out of the box, right? So minus, now we are putting the limits, right? So first of all we are putting the upper limits minus lower limits, right? So ln 1 minus xa minus ln of 1. Okay, now ln of 1 is 0, right? Ln of 1 is 0. So we are remaining with the minus ln of 1 minus xa is equal to minus ln 1 minus xa. I hope you have understood. So the answer of this integral form is integration of 0 to xa dxa upon 1 minus xa. The answer is minus ln 1 minus xa. I hope you have understood how we have solved and understand how to solve this integral form, right? Okay, so now we can put this answer, plug in this answer in the above equation, right? So volume of PFR is equal to Fa naught into minus ln of 1 minus xa minus ln of 1 minus xa divided by K Ca naught, right? So here we have formulated the volume, right, required, okay, for the plug flow reactor. So we have all the values of initial molar flow rates, conversion, rate constant K, initial concentration. We need to just plug in all the values. So Fa naught we have as 6 moles per hour. Okay, we have the conversion as 0.90. Okay, we have the rate constant value as 0.0002 second inverse. The concentration we have the value as Cn naught is equal to 0.4 moles per cubic decimeter, right? So plug in all the values. Okay. Similar way from the so volume of PFR is equal to 6 moles per hour into minus ln of 1 minus 0.90 upon K 0.0002 second inverse. Cn naught has 0.4 moles per cubic decimeter, right? So we have plug in all the values here, right? So from the denominator, from the numerator and denominator, we can cancel off moles, right? We need to also cross verify the unit conversion, right, with the solving, right? So let's say here we are remaining with the our seconds in decimeter cubic decimeter, right? So denominator to its denominator will come to the numerator, right? So due to those reasons, the cubic decimeter will come to the numerator. Here in denominator we have second inverse, which means in denominator we have 1 by second. So denominator to its denominator will come to the numerator. So seconds will come in the numerator, right? Similarly way in the numerator we have moles per hour, which means we have hours in denominator. So due to those reasons, hours will come to the denominator, right? So let's say we are calculating the volume. So we require the volume in terms of cubic decimeter or liters, right? So we need to do unit conversion, right? So let's say, so here we need to cancel this s and hour. So how will do? So we'll multiply with 1 hour divided by 3600 seconds, which means in 1 hour we have 3600 seconds, right? So by multiplying these down, the hour from the numerator and denominator can be cancelled off. The seconds from the numerator and denominator can be cancelled off and will remain with the cubic decimeter, right? I hope you have understood. Okay. So after solving these, you will get the answer as volume of PFR is equal to 47.970 cubic decimeter is equivalent to 48 cubic decimeter is equal to 48 liters, because 1 cubic decimeter is equal to 1 liter, right? So 48 cubic decimeter is equal to 48 liters, which means in order to achieve the 90% conversion by using the first order reaction kinetics, by keeping all the operating parameters to be constant, and in order to achieve the 90% conversion by using plug flow reactor, we required 48 liters volume of plug flow reactor. I hope you have understood, right? Okay, now we know how much volume, how large volume of plug flow reactor is required in order to achieve the 90% conversion, right? But yet we don't know how much time will it take in order to achieve the 90% conversion, right? So let's understand that and let's get started to calculating how much time will it required, right, in comparison with the plug flow reactor and the CSTR. So we can calculate the time required for the plug flow reactor by using the space time. So space time is denoted as tau, is the ratio of volume to its volumetric flow rate. The volume of the plug flow reactor is 48 cubic decimeter, right? So 48 cubic decimeter divided by volumetric flow rate, which is 15 cubic decimeter by hours, right? So 15 cubic decimeter by hour. So from the numerator and denominator, the decimeter can be cancelled off and will remain with the hours, which means after solving these, you will get the answer is the tau of PFR, the space time of PFR is 3.2 hours, which means 3.2 hours, which means by keeping all the operating parameters constant, by solving for the first order reaction kinetics, by using the plug flow reactor, we required 48 liters volume of plug flow reactor and 3.2 hours time in order to achieve the 90% conversion. Okay, I hope you have understood. Okay, I hope you have understood up to here, right? So I request you to please make all these notes. Okay, now let's say, now what if instead of, in comparison and instead of CSTR plug flow reactor, what if I use batch reactor? Then what if I design the batch reactor? How large volume of batch reactor is required? What will be the space time? Right? So let's understand that, right? So let's get started. So in the third part, we are using the batch reactor. In similar way, we are keeping all the operating parameters to be constant, identically the same. We are using the same first order reaction kinetics with the given rate law has minus RA is equal to KCA, right? Where the K is equal to 0.0002 second inverse, right? So how large volume of batch reactor is required in order to achieve the 90% conversion? How much time will it require in order to achieve the 90% conversion, right? So we'll understand and calculate that, right? So let's say the first step is to write the performance equation of the batch reactor, right? The performance equation of the batch reactors is indicated by T is equal to Ca naught integration of 0 to xa dxa upon minus Ra. Okay, so we will try to modify the performance equation, right, based on the given data. So let's say minus Ra can be written as Kca. So T is equal to Ca naught integration of 0 to xa dxa upon Kca, right? Now similar way here, what form of Ca we need to utilize, right? So again, don't get confused. We are trying to derive the performance equation, right? We are trying to derive the performance equation. We are trying to formulate the performance equation. We are trying to derive the reaction rate. So remember that whenever we are trying to derive the reaction rate, the performance equation, we are trying to formulate the performance equation, we'll always use the second form of the Ca, right? Okay, so we'll always use the second form of the Ca, which is the fundamental relationship and is always correct. Okay, and is always correct. Okay, and the second form of Ca is defined, defines the conversion, right? The Ca also defines the concentration of reactants at any point of the batch reactor. Okay, so due to those reasons, we will use the second form of Ca in order to modify the performance equation of the batch reactor. I hope you understood, right? So we'll use the second form of the Ca. Okay, so let's say T is equal to Ca naught divided by K. Now why K? Ca naught divided by K, because K is constant, right? We have the value of K has 0.0002 second inverse. Due to those reasons, we can take K out of the integral, right? We can take K out of the integral. So Ca naught divided by K, integration of 0 to xa dxa upon Ca. Now we are writing Ca has Ca naught into 1 minus xa. So Ca naught into 1 minus xa. I hope you understood, right? So T is equal to Ca naught divided by K, integration of 0 to xa dxa upon Ca naught into 1 minus xa, right? Now similar way, Ca naught is constant. Initial concentration of reactants A is 0.4 moles per cubic decimeter, right? So due to those reasons, we can take Ca naught out of the integration, right? So Ca naught by K, Ca naught integration of 0 to xa dxa upon 1 minus xa, right? So say, from the numerator and denominator, we can cancel off Ca naught. So will remain as, so let's say now we need to again solve these integral from, right? So we have already solved here, right? So similar way, we can solve this integral form and we can get the value of this integral form as minus ln 1 minus xa, right? So we'll use the same procedure to solve the integral form, or we will remember, let's say if we have this type of integral from integration of 0 to xa dxa upon 1 minus xa, then the answer will be minus ln 1 minus xa. I hope you have understood, right? So finally we can formulate it as t is equal to minus ln 1 minus xa divided by k, right? Now we need to just plug in all the values. xa is 0.90, right? We need to achieve the desired conversion of 90%, 0.90. Okay, k value is 0.0002 second inverse. Okay, now let's say here we have second inverse, right? So one in denominator we have 1 by second, so second denominator of denominator will go to the numerator. So in numerator we have seconds, right? So we need to convert, we need to also cross verify the unit conversion, right? So for the unit conversion we are multiplying it by 1 hour divided by 3600 seconds, right? So seconds in the numerator and the seconds in the denominator will get cancelled off. Okay, and we will remain with the hours. Okay, I hope you have understood. Now after solving this, you will get the time required for the batch reactor is 3.198 hours, which is equivalent to 3.2 hours, which means in order to achieve the 90% conversion by keeping all the operating parameters to be identically same, by using the first order reaction kinetics for the given rate law minus Ra is equal to Kca, by using the batch reactor we required 3.2 hours of time in order to achieve the 90% conversion, right? I hope you have understood. Okay, so here we have calculated the time required to achieve the 90% conversion by using the batch reactor, but we yet don't know how large volume of batch reactor is required in order to achieve the 90% conversion, right? So let's understand how we calculate the volume of batch reactor. Okay, we can calculate, right, how the volume of batch reactor is calculated, right? So by using the concept of the space-time, we can calculate the volume of the batch reactor required to achieve the desired conversion of 90%. So space-time is the ratio of volume to its volumetric flow rate, right? So here we are aiming to calculate the volume of the batch reactor side. So we are making the subject as volume of the batch reactor is equal to tau into V naught, right? So here we know the value of tau. Tau is the space-time. Time for the batch reactor is indicated as tau, which is 3.2. So volume of batch reactor is equal to 3.2 hours into volumetric flow rate, 15 cubic decimeter per hour, right? Volumetric flow rate 15 cubic decimeter per hour, right? So let's say by solving these, so let's say here in numerator we have hours and in denominator we have hours. So hours will be cancelled off from the numerator and denominator. By solving these, we'll get the answer as volume of batch reactor is equal to 47.97 cubic decimeter is equal to 48 liters, which means in order to achieve 90% conversion by having the first order reaction kinetics for the given rate law minus Ra is equal to Kca, and by using the batch reactors we required 48 liters volume of batch reactors and 3.2 hour time in order to achieve the 90% conversion by utilizing the batch reactor, by designing the batch reactors, right? I hope you have understood. Okay, right? I hope up to here you have understood. Okay, so I request you to please make all the notes. Okay, now but there is common mistakes which all the students make, right? So can you guess what is the common mistakes the students make here in this calculation, right? So let's say, let me help you to, I will direct you to understand, analyze and calculate, okay, and to understand what is the common mistake which students make, right? Easily make. Okay, so let's say here if you see, let's say for example the calculations by using the performance equation is correct in all the industrial reactor designs, right? Okay, but the calculation of volume of the industrial reactors, we are calculating it by using the space-time, by using the fundamental concept of the space-time, right? So space-time is the ratio of volume by its volumetric flow rate. Okay, so let's say the space-time calculation with respect to all the industrial reactors, right? The term space-time is correct for all the industrial reactors. Okay, the the term volume is correct for all the industrial reactor, right? Whether it may be batch reactor or whether it may be continuously flow reactor, right? Both the term space-time and volumes are correct for the individual industrial reactors. Okay, now here the term volumetric flow rate. Now here the term volumetric flow rate. This is exactly where the students make mistakes, right? The volumetric flow rate is the where the students make easily mistakes, right? So let's say volumetric flow rate, which means what? The By using this concept, we have solved the volume of the batch reactor, right? So the concept is correct, but the calculation is partially wrong, right? The calculation of volume of batch reactors is not correct here. Okay, this is exactly where the students make the mistakes, right? So why? We'll understand that. Let's say volumetric, the space time is okay, volume is okay, right? But volumetric flow rate, which means volumetric flow rate we have has volumetric flow rate of 15 cubic decimeter per hour, which means volumetric flow rate, which means the volume of the fluid which is entering into the reactor in the reaction environment. The reaction will take place and will get converted into the new product, and that product will exit through the outlet stream, right? I hope you have understood. Okay, which means see the units, understand the units. The volumetric flow rate is 15 cubic decimeter per hour, which means 15 liters of volume of fluid will enter the reactor via inlet stream. In the reaction environment, the reaction will take place, and same 15 liters of volume of fluid will exit through the outlet stream of the reactors, right? Okay, with respect to each and individual hours, which means the volumetric flow rate indicates the continuous flow, right? Which means for the first hour 15 liters volume of the fluid will enter into the reactor and the reaction will take place, and 15 liters volume will exit through the outlet stream of the reactor. Again in the second hour, the 15-liter volume of the fresh feed will enter into the reactor via inlet stream. In the reaction environment, the reaction will take place and will get converted into the new product, and that fluid will exit through the outlet stream of the reactors in the second hour. Similarly, in the third hour, 15 liters volume of the feed will enter into the reactor, reaction will take place, and the fluid stream will exit through the outlet stream of the reactors, right? So the volumetric flow rate indicates the continuous flow reactors, right? So for the case of batch reactor, we are using the volumetric flow rate. So here is the twist, right? So this concept is partially correct, but we cannot use this concept for the calculating volume of the batch reactors, right? Because we have two types of reactors. In batch reactors, we have batch reactor and continuously flow reactors. The continuously flow reactors are CSTR, PFR, packed bed reactors, fluidized bed reactor, right? Are the continuously flow reactors. In continuously flow reactors, the feed stream will enter continuously to the reactor. The reaction will take place continuously, and continuously we have the exit of the product stream out of the reactor via outlet stream, right? Which means we have continuously inlet to the reactor and we have continuously outlet to the reactor, are called the continuous reactor. But in batch reactors, we have a one-time feed entering into the reactor, and afterwards the feed will stop entering into the reactor and the reaction will take place. And after the completion of the reaction, the fluid stream will the fluid or the product stream will exit through the reactor in single go, right? Means only fluid stream will enter into the reactor and there will be no outlet stream, right? Reaction will takes place, the reaction gets complete, and afterwards the outlet stream will switch on and the fluid or the products will exit through the outlet stream, right? It is a single way, inlet once time and outlet once time. It's called the batch, right? So due to those reasons, by using the concept of the space-time, we cannot calculate the volume of the batch reactor, right? So then how to calculate the volume of the batch reactor? We'll understand that, right? So up to here, I request you to please make all the important points, right? I request you to please make all the notes, right? And we will continue the solution, right? In the lecture number, in the previous lecture, lecture number 13, in the similar manner, we have calculated the volume of the batch reactor, which is incorrect. Partially correct. Conceptually it is correct, but partially it is incorrect, right? So same way, we'll use the same zeroth order kinetics and we'll try to solve the batch reactor volume. And for this case also, we'll try to solve for the first order reaction kinetics, how much volume of the batch reactor is required, right? And we'll try to also solve what if we design the packed bed reactor instead of CSTR, plug flow reactors or batch reactors, then how much for the same all operating parameters conditions, right? We will keep all operating parameter conditions to be identically same. We'll use similar first order reaction kinetics for the given rate law has minus RA is equal to KCA, and we'll try to solve for the and we'll try to design for the packed bed reactor, like how much, and we'll try to compare how much volume of the reactor, how much space time, and how much weight of the catalyst is required in order to achieve the desired conversion of 90%. Okay, so I request you to please make all the notes. Okay,